Okay, next on our agenda is derivative-free methods. These are especially relevant for what's called black box optimization. So for instance, if we assume that the policy, our policy function that we would like to optimize is either non-differentiable, so we cannot compute its derivative, or right here, example of non-differentiable functions, or that we don't, or if it's a black box, we don't know how that function works. We can just observe the input and output. So we'll discuss those derivative-free methods for black box optimization. Question, yeah?
How is that different from optimizing a neural network, which also we just see an input and output? Is that not a black box as well?
Okay, so that's a good question in order to just clarify what we're doing. So in a deep neural network, yes, we're also training, if we're just looking at it as a supervised learning problem, we're getting some input and some level output. We're just observing the input and output and trying to fit the deep neural network, for instance, to output the specific output that we expect to see. However, this is not a black box optimization problem, because we know the internal structure of the deep neural networks. We know the architecture. We know how everything is connected, the neurons and the activation function. So much so that we can actually do a backpropagation algorithm. We can actually compute the derivative of all of the tunable parameters with respect to the output. Right? We don't assume that in black box optimization. When we perform black box optimization, we assume that we can only observe the input, or given some input, we can then observe the output. We can tune some parameters. We cannot compute the derivative with respect of those the derivative of the output with respect to those parameters, or anything like that. We don't know anything about the structure of the function. We don't even know that it is differentiable, right? And of course, a deep neural network is differentiable. I mean, more than that, we know how to compute its derivative, its gradient. Okay, finally, as we approach the end of the semester, with respect to your final report, please limit your final report to 6 pages. Usually, you should be able to fit whatever you wanna tell us within 6 pages. If it's more than that, then probably you're overdoing something or over-explaining something. Please try to be concise and on point, right? We don't want to struggle in order to understand exactly what you did. You can be very much on point, right? With bullet points and numbering, and be very clear and try to follow a very clear narrative, a very clear story, right? What is the problem? What is the research question or your hypothesis? What do you hypothesize? And the setting and your results, and then maybe a discussion on the results. But please be on point, okay? Okay, so next let's start discussing our derivative-free approaches for gradient-free approaches for black box optimization. So in the grand scheme, this is where we stand. So we already covered, actually, I think we started by covering temporal difference learning, and we saw how to do value-based reinforcement learning, specifically Q learning, based on one-step TD learning or n-step TD learning or lambda returns and so on. We saw several approaches. We also saw policy iteration approach that uses TD learning in order to compute value functions or Q values for a specific policy and then improve the policy, right, and work in iterations. We also discussed how to tune a policy approximation. Specifically, we saw the policy gradient theorem and how to, well, what's the correct direction to update our policy. We combine policy gradient with policy iteration to produce an actor-critique approach, actor-critique algorithms. Today, we're going to tune our policy, but without assuming to know its gradient, without even assuming to know that it's differentiable. This might be relevant if we have a non-differentiable policy, and specifically, in that case, we're going to today we're going to cover gradient-free methods. By the way, this is not necessarily just for a policy, it can be not necessarily for a control function, it can be really any optimization where we're trying to find several optimal parameters for any objective function. Okay, we'll see some examples of that. So what does this mean? In practice, how will this process work? So we'll still do online parameter tuning, right? We'll have a set of parameters that we would like to tune, and then to somehow we assume to be able to observe the output of our black box function and how it performs in the real world. Okay, so we'll start by setting the parameters, all of the tunable parameters. This can be weights and biases in a deep neural network, although that's, again, we don't need to do it for a deep neural network because there we can, it's not a black box optimization problem. And actually, usually we don't want to, if the dimensionality of the parameters that we need to tune is very high, these approaches don't work very well. I'll explain why in a second. So normally we consider a fairly small set of parameters, not too large. So a limited dimensionality. We set it initially arbitrarily. We evaluate the parameters in the real world. If it's a policy, we act in the real world. We observe the outcome, the performance. We evaluate that, and we use this evaluation in order to tune our parameters. Okay, so something very similar to online learning that we've seen before in reinforcement learning. Specifically, we're going to discuss three methods today. We're going to discuss gradient approximation. So this gradient approximation even doesn't require us to be able to compute the gradient. We'll just approximate it by looking at the outcome. It doesn't even require that our objective function is differentiable. So we'll approximate the gradient even if it doesn't exist. We'll do this by using a finite difference approach. This is a known approach in mathematics. Specifically in our case, we will use the RL version of a finite difference approach, which is known as finite difference policy gradient descent. Next, we're going to discuss some genetic algorithms, specifically a very specific evaluation strategy, actually one that is very powerful, still presented in 1996, but it's still, I would say, a go-to black box optimizer that is used quite commonly, even these days. Actually, also in my lab, I'll show you some papers by my students that used CMAES, covariance matrix adaptation evolution strategy, and obtained good results, state-of-the-art results. Finally, we'll discuss Gaussian processes, which are relevant when the sample cost is very, very high, and we have to be very frugal, very to try to minimize the number of samples that we obtain. What else do I want to say about this? So the important thing in all of these is these are online tuning. What does it mean? It's not supervised learning, because we are able to decide on the next samples that we're going to collect, right? We are able to set the parameters and then see the output. And then we can set different parameters, but we choose that. So we want to choose that in a clever way that will allow us to converge to the optimum of the function that we're trying to optimize. Okay, so let's try to define this notion mathematically, the problem that we are trying to address. So we would like to minimize some function, and this can be, if we're trying to tune a policy, what will we try to minimize? Minimize
loss, maximize the reward.
Negative J, right?
Yes.
The J function, yeah. We're trying to maximize the reward of the policy, but this is a black box optimization is more general than just optimizing a policy. Right, so we'd like to minimize some function. Again, we might say we want to maximize some function. It doesn't really matter, right? Of course, for optimization, which maps some dimensionality of input values. We'll consider those as continuous, as a real valued number, okay, with n dimensions, and that will map to some a scalar representing the utility of function f. And of course, well, we'd either like to find the assignment that minimizes the output or maximizes it. Again, it doesn't matter. Without loss of generality, let's just say minimize. So we would like to compute the optimum of f of x, or where is it with respect to x. If our function is convex, no problem, we can solve it in a closed form solution, right? Assuming that we know x. We can just set the gradient of our function to zero, and then solve using common optimization techniques, Lagrange method, KKT, and so on. Else, if it's non-convex, we can still use gradient descent approach, right? Like an Adam optimizer or Newton methods, if you can differentiate it twice, and reach at least a local optimum, right? But the problem that we are trying to address in black box optimization is, what if f is unknown and we can only sample f of x for a given x, but we cannot compute, we don't know anything about the function, we certainly cannot compute any gradients with respect to that. So these approaches just won't work. We cannot apply those. Can we approximate f with supervised learning and then apply this approach? So this might be a reasonable solution. The problem is that the observations are not provided. We cannot just train an approximation of the function. We must learn from interactions. We might get some samples initially, but normally in the general case we don't. And we can choose where we want to sample and continue that process in iteration. And of course, we would like as much as possible to minimize the number of samples. So in that case, you might say, well, okay, you can just use reinforcement learning. This is exactly what we're doing in reinforcement learning. We don't get initial observations, but we can interact with the environment and obtain some performance measurement. So yes, usually we do use reinforcement learning, but in our case, in the black box optimization case, the function is unknown or not, maybe it's known, but not differentiable, right? So we cannot do this simple optimization technique. Actually, for most cases, we'll just assume that it is unknown. It's a black box, right? We don't know anything about that. We can just control the input and observe the output. And this is exactly where we use black box or black box optimization. Specifically today, we're going to discuss derivative-free methods to do that. So some examples of where we might use black box optimization. And these are just two specific examples from my lab, recent examples from my lab, where we had one of my students, Sumed, helped or joined forces. We joined forces with a professor in architectural engineering, and they tried to optimize the design of a room, of the windows and shading, to optimize light conditions. So it will be lit, and you can conserve energy, but you won't be, there will be minimal glare, and there are all kinds of different dimensions that they need to optimize together and get a very good performance in the room. So they can run simulation and test a given setting of the room, but they cannot compute the gradient with respect to this utility that they're measuring with respect to the different parameters that they can set in the room. So in this case, we specifically used CMAS, as I said before, and obtained state-of-the-art results for optimizing indoor daylight in different rooms. Another example is actually again by led on our side by Sumed, one of the PhD students in my group. He worked with a company, a video game company, Niantic, right? That wanted to come up with an automated way to optimize meta in video games, which means how to set the statistics of the different tools or
game balancing.
Right, for game balancing such that as a player will be incentivized to, all tools will have some equal value. So all of them might be used in some sense. So we won't have like a strong character that we always choose, but we'll try to balance all of them. Of course, without having a degenerate solution, we just assign the same powers to all of them, on diverse powers, while making them balance with respect to their appeal to the player. So this is also a good example where we have a specific objective function, a complicated one, but one that relates to the appeal or to the how much the players actually use each one of the tools or characters. And we have some input that we can control, which is the statistics of each item or character. And again, in this case, as far as I remember, we also used CMAES as a black box optimizer. Okay, so finally, when we perform black box optimization, there are several challenges. We like to, of course, as I said before, we like to compute the optimum of an unknown function using just samples from that function. Usually we try to be sample efficient. This is very important. In some cases more than others. Some cases samples are very expensive. That is, we would like to minimize the number of samples along the training process. And in many cases, this is also something that operates in the real world. So we would also, in many cases, would like to minimize cumulative regret. Right? Hopefully you remember what's regret. It's like the area under the curve for each one of the training function. About the area under the curve, I mean, it has a more specific definition, which we previously discussed already. But right, so it depends on the domain. In one domain, maybe you're willing to learn maybe slower initially, as long as you get to very good performance after many iterations. While in another domain, you'd like to perform very well quickly, and you don't care how fast, or you care less how fast you reach to the asymptotic optimum.